Welcome to properties of limits of sequences. So here we're going to assume that the limit as n goes to infinity of a sub n and the limit as n goes to infinity of b sub n exist. Then the sum or difference of sequences tells us that if c sub n is a sub n either plus or minus b sub n, then the limit as n goes to infinity of c sub n is simply equal to the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n. So we had this exact same rule with regular limits. It makes sense that it should apply for sequences as well. Similarly for products, if c sub n is equal to a sub n times b sub n, then the limit as n goes to infinity of c sub n is equal to the limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. Again, same thing, we could split limits across products as long as the individual limits existed. For quotients, if we take c sub n to be a sub n over b sub n, and the limit as n goes to infinity of b sub n is not equal to 0, then the limit as n goes to infinity of c sub n is simply the limit as n goes to infinity of a sub n over the limit as n goes to infinity of b sub n. So here again, we're just splitting the limit across quotients as long as they exist and the bottom limit is non-zero. This works. And then our last main rule for limits was the scalar multiple of a sequence. So if c sub n is equal to some constant times a sub n, where capital C is a constant, then we have that the limit as n goes to infinity of c sub n is simply equal to capital C times the limit as n goes to infinity of a sub n. So again, these are the same rules we had for regular limits, which makes sense since the limit matches just the function if we extended the function to all values instead of just the counting numbers. All right, so now for some practice. I gave you 3 sequences and their limits. So a sub n equaling n over 2 to the n. This limit as n goes to infinity goes to 0. B sub n equals 2 to the n plus 1 minus 5, all over 2 to the n. This limit as n goes to infinity is 2. And then last up, c sub n equals 1 plus 1 over n, all raised to the nth. This limit is e. So if I wanted to find the limit as n goes to infinity of a sub n minus 2 times b sub n, this should be precisely the same thing as taking the limit as n goes to infinity of a sub n, and then subtracting off 2 times the limit as n goes to infinity of b sub n. So here I've split across the subtraction, pulled out the scalar multiple. So a sub n had a limit of 0. So we have 0 minus 2 times b sub n had a limit of 2. So we wind up getting -4 as our limit. Next up, let's look at the limit as n goes to infinity of b sub n times c sub n. So this should be the same thing as the limit as n goes to infinity of b sub n times the limit as n goes to infinity of c sub n. B sub n had limit 2, C sub n had limit e. So this is just 2 times e, or 2e. So again, this is how we can go about evaluating limits of slightly more complicated functions if we can split it into ones that are easier to evaluate. All right.